This is Swathi, working as Assistant Professor in Institute of Aeronautical Engineering in the Department of Electronics and Communication Engineering. Welcome to the lecture. In this lecture, we'll discuss rectifiers and half-wave rectifiers and its mathematical analysis of half-wave rectifier. First of all, what is a power supply and what is a need for a power supply? And here, why we are discussing this need for power supply is the rectifier is the major block of power supply, regulated power supply, which plays a vital role in converting AC into DC. So what is the need for power supply? So most of the electronic devices such as computers, televisions, cathode ray oscilloscope, etc. Every home, not only this, every home appliance will require DC voltage, DC power supply. Whereas we are getting AC supply from the mains. So that is of 230 volts and 50 hertz AC supply. So in order to make compatibility between the AC supply and our electronic appliances, so we need to convert that AC supply which we are getting from the mains into DC. So for that we are going for the regulated power supply. So here we can convert our 230 volts AC supply into any required voltage level, like 12 volts DC or 30 volts DC or 9 volts DC or 5 volts DC by using this regulated power supply. So what are the major blocks of this regulated power supply? So the basic building blocks of regulated power supply are the transformer, next rectifier, smoothing, or else we can smoothing circuit, or we can also call it as a filter circuit, and then regulator, and then the load. So first of all, what is the importance of a transformer? Transformer, an input transformer for the stepping down. So this transformer is mainly used to stepping down the AC supply of 230 volts into our required level. So coming to the rectifier. So the rectifier is a circuit which is a major part of a regulated power supply. So which is used to convert AC supply or else AC components present in the signal into DC components. So this is a major block which converts AC supply into DC supply. And smoothing filter. So even though the rectifier converts AC into DC, but we are not going to get the pure DC as output from the rectifier. It also contains some AC components. In order to remove that AC components present in the output of the rectifier, we are using this smoothing circuit. We can also call it as a filter. So filter is a circuit which smoothens the variation present in the output of the rectifier. The next block of regulated power supply is regulator. So a voltage regulator circuit maintains a constant DC output voltage irrespective of the changes in the load or in the current. Next, load. Load is a circuit which uses the pure DC form from the regulated power supply. This load may be any of our electronic appliances like either fan or AC or TV, whatever it is. So this is the major block of these are the major building blocks of regulated power supply. So here in the circuit I have shown the input and output waveforms of each and every block. So the transformer to which we will be getting input as AC, and the output of the transformer is also AC, but it will be reduced, that the voltage level will be reduced to our desired level. And the rectifier which converts our AC into DC. So here DC means actually we have to get a constant supply even though there are variations in the time. So we should not have any variations in the voltage. This is voltage or either power or current. So here the output of the rectifier is not a pure DC, which is having only positive half cycles of AC signal. So means it is having AC components and DC components. So that is why this is called as pulsating DC. This is called as pulsating DC. And if I give this pulsating DC as input to the filter, so the AC components will be reduced for up to some extent, and the output of the filter will be having only little amount of ripples like this. So this is the filtered output. Still it is having some AC components. So in order to get a constant DC supply, we are using a regulator, so which produces a constant DC supply even for the variations in the input current. So this is the output of the regulator, which is to be given to our load. So this is the basic building block of a regulator power supply. So as I told you, first transformer. So the transformer is having two coils, primary coil and secondary coil. So the output of the transformer is connected to the rectifier circuit from the secondary winding. So here we have two types of transformer. One is step up transformer and the second one is step down transformer. So in the design of our regulated power supply, we generally prefer step down transformer because we are going to step down the voltage of 230 volts into our reduced level, that is our required level. So that is why we always prefer step down transformer. So step down transformer is a transformer in which the secondary winding has less number of turns when compared to the primary winding. So this is a primary winding where the number of turns is more when compared to the number of turns in the secondary winding. So let us have some notations here. Let us indicate IP, the current flowing in the primary of the transformer, and IS is the current flowing in the secondary winding of the transformer. VP is the voltage drop across the primary winding of the transformer, and VS is the voltage drop across the secondary winding of the transformer. Even we can, instead of representing with IP, IS, VP, VS, we can also represent that with I1, I2, V1, V2 respectively. So this is step down transformer is most preferable, most commonly used transformer in the rectifier. So now let us enter into the topic, that is rectifier. So the output of the step down transformer, according to the block diagram, the output of step down transformer is given as input to the rectifier. So what is a rectifier? Rectifier is a circuit which converts alternating current input power into direct current output power. That means it converts AC input power into DC output power. So depending upon the period of conduction, rectifiers are basically classified into two types, half wave rectifier and full wave rectifier. This is based on the conduction period of diodes. We are going to classify the rectifiers into half wave and full wave rectifier. So depending upon the connection procedure, we have another type of rectifiers. That means the full wave rectifier is again classified into two types based on the connection procedure. So that is center tapped full wave rectifier, center tapped full wave rectifier, and the second one is bridge full wave rectifier. So this classification is based on the connection procedure. We are classifying the full wave rectifier into two types. One is center tapped full wave rectifier and bridge full wave rectifier. So now first let us have a discussion on half wave rectifier. So the process of removing one half of the input signal to establish DC component is called as half wave rectifier. We can also define the half-wave rectifier in other way. The rectifier circuit which rectifies only half cycle of the input AC signal is known as half-wave rectifier. And here in this half-wave rectifier, the diode conducts only during the positive half cycle of input signal. So the input signal is AC, which is alternating current, which varies sinusoidally with respect to time. So as I'm saying that in a half-wave rectifier, diode conducts only during the positive half cycle of input, whereas a negative half cycle is going to be removed, and hence this is called as half-wave rectifier. That means it is a circuit which rectifies only positive half cycle of input AC signal, and hence it is called as half-wave rectifier. So this is the basic circuit diagram of half-wave rectifier. So this is a step-down transformer. So where we have more number of turns in the primary winding and less number of turns in the secondary winding. And so from the primary, we will be getting AC supply, which is of 230 volts and 50 hertz. And based on the turns ratio, it is going to be reduced to our required level. And here in the secondary winding, we have a diode connected to the upper terminal of the secondary winding of the transformer, and to the cathode of the diode, we have connected a load resistor RL. And the load resistor RL is connected to the lower terminal of the secondary winding of the transformer. So this is half-wave rectifier, which uses only a single PN junction diode. Now let us see how this rectifier operates. So during the positive half cycle of input voltage. So during the positive half cycle of input voltage, as I said, input is AC signal, which is having positive and negative half cycle. So during the positive half cycle of input voltage, point A becomes more positive, point B becomes more negative. So the anode of the diode is connected to point A, which is at more positive potential during the positive half cycle of input voltage. This diode is forward bias. When the diode is forward bias, it will be short circuited, and it offers a very low resistance, that is forward resistance RF, and it is short circuited. So now this is the equivalent circuit of the half-wave rectifier during the positive half cycle of input AC signal. So during the positive half cycle of input signal, point A of the secondary winding becomes positive and point B becomes negative, which makes the diode D forward biased, and hence it will be short circuited and offers a very low resistance, that is a very low forward resistance RF. So when it is short circuited, definitely there is some current flowing through this circuit. And if you observe these two, this offers a small resistance RF, which is connected in series with RL. So as all of these are connected in series, same current flows through the circuit. So as the diode is forward biased, it is short circuited, and hence current starts flowing through the load resistor. So as the input is varying sinusoidally with respect to time, so the current through the load resistor will also vary sinusoidally with respect to time, which leads to a sinusoidal output voltage across the load resistor. So IL is the current, okay, and V out is the voltage drop across the load resistor. So here we are calculating the DC output voltage across the load resistor. So this is the operation during the forward bias, positive half cycle of input. Next, what happens during the negative half cycle of input? So let us go back to the circuit again. So during the negative half cycle, this point A becomes negative and point B becomes positive. So as point A is negative at more negative potential, whereas the diode anode is connected to point A, so we are applying negative potential to anode of the diode, and hence this makes the diode reverse biased. So we are applying negative potential to the anode, which is positive terminal, which makes the diode reverse biased. When a diode is reverse biased, it offers infinite resistance and it will be open circuited. When the diode is open circuited, there is no path for the current to flow and hence no current flows through the load resistor. As there is no current flowing through the load resistor, so the output voltage across the load resistor is also considered to be 0. So that is why we are getting 0 output voltage across the load resistor, as there is no flow of current through the load resistor, because during the negative half cycle of the input signal, the diode is reverse biased and it is open circuited. So that is why it causes 0 output voltage across the load resistor. So here during the positive half cycle, we have got positive cycle of output voltage, and during the negative half cycle of input voltage, we have got 0 output voltage across the load resistor. As the input is alternating in nature, again it repeats. So again for the for positive half cycle, diode becomes forward biased and hence we'll get a positive half cycle of output, and during the negative half cycle, it is open circuited. So like that. So here let us have a let us have a look at the output waveform here. This is the input. So here positive half cycle is having a duration of 0 to pi and negative half cycle is having a duration of pi to 2 pi, and this is 3 pi and this is 4 pi. So what output we are getting during the positive half cycle? 0 to pi we have sinusoidal output, and during the pi to 2 pi we have 0 output. So let us have this as maximum voltage or peak value. Let us represent this one as V maximum, that is plus V max, and this one as minus V max. So during plus V max, that means during the positive half cycle, the output is also equal to the input. So that is why we'll get plus Vm output across the load resistor. So this is the operation of half wave rectifier. And so as if you observe the output waveform, it is only rectifying positive half cycle and it is completely removing the negative half cycle. So that is why this rectifier is called as half wave rectifier. And also you can remember the diode conducts only during the positive half cycle and non-conducts during the negative half cycle of input. So now let us go to the mathematical analysis of half wave rectifier. Why we have to go for mathematical analysis? In order to analyze various characteristics of a rectifier, we are doing some mathematical analysis. So for analyzing the various characteristic parameters of half wave rectifier, first of all, let us consider the input. So as I told you that input is sinusoidal, that means alternating current, which is varying sinusoidally with respect to time. So here this can be mathematically. So as I told you that this is plus Vm and this one is minus Vm. So here we can mathematically represent this sinusoidal input AC signal as Vi is equals to Vm into sine omega t, where Vm is the maximum value of supply voltage. What kind of supply voltage it is? AC supply voltage. Now let us assume the diode as ideal. If it is ideal, then we can consider that RF is equals to 0. That means forward resistance offered by the diode is equals to 0 and the reverse resistance offered by the diode is equals to infinite. So let the forward resistance of the diode as RF when the diode is on. This is offered only when the diode is on, and this happens when the during the positive half cycle of input. And the reverse resistance is represented with RR, which is offered by the diode when it is reverse biased and it is off. So when the diode is forward biased, there will be a flow of current, and under reverse bias condition, there is no current flowing through the load resistor because the diode is open circuit. And hence we can also, as we know that the current waveform is also given by this one. This is the current through the load resistor, which is indicated with IL or else I. So that is 0 to pi. Again, I can represent this as Im sine omega t, whereas pi to 2 pi it will be considered as 0. So that is how the current I in the diode or load resistor is given by I is equals to Im into sine omega t for 0 to pi. Actually it is pi, not 2 pi. And for I is equals to 0 for pi to 2 pi, pi less than or equals to omega t less than or equals to 2 pi. And as I told you that when the diode is forward biased, it offers a resistance, forward resistance, and load resistance is connected in series. And here we have an AC supply that is plus minus Vs. So the current is flowing here. Okay. And here this is given by Vm sine omega t. And the current I can be given by I is equals to Vm divided by Rf plus Rl. That is input voltage divided by total resistance. Why this total resistance is considered as Rf plus Rl? Because these two are connected in series. So Im, that is Im is equals to Vm divided by Rf plus Rl. If we have considered an ideal diode, then Rf is equals to 0. In that case, Im will be taken as Vm by Rl. These things we have to remember. So this is the current through the circuit or diode or through the load resistor. Now, for doing the mathematical analysis, first we need to find out the DC output current and also the DC output voltage which is measured across the load resistor. So here the DC output current or voltage is also called as average current or average output voltage. So how can we find out the average output voltage? So here this is the waveform of either current through the load resistor or voltage across the load resistor. So let us have this one as IL. So which is having Im, maximum value of Im 0 to pi 2 pi. So the average value of current can be found out by finding or else the DC value of current can be found out by finding the average value of this one. That means area under this curve will give you the average value of this current. So the area under the curve, so that is IDC. So as we always get the DC output voltage across the load resistor, so we are representing it as IDC, can be obtained by 1 by 2 pi integral 0 to 2 pi IL d omega t. IL d omega t. So here that means this represents the area under the curve for a duration of 0 to 2 pi. That means for a complete cycle, whatever the area under the curve represents the average value or else the DC value of output current, which is represented by IDC. So now let us split the limits here. So that is 0 to pi IL d omega t, already according to the equation Im into sine omega t, and for pi to 2 pi it is 0. So 0 to pi Im sine omega t d omega t plus integral pi to 2 pi, the current is considered to be 0 d omega t, right? So now let us, this one becomes 0 because IL is 0 during pi to 2 pi. So now let us take Im as constant out. So 0 to pi sine omega t d omega t. So the integration of sine. So I can take this one as Im by 2 pi. Integration of sine is minus cos omega t and the limits are from 0 to pi. So now just substitute the limits here. Im by 2 pi minus of cos pi. Cos pi is minus 1. So it is minus 1 minus of minus cos 0. It is 1. So now this becomes Im by 2 pi minus of minus. This is plus 1 and this one is also plus 1. So it is Im by 2 pi into 2. So this one get cancelled. So that is Im by pi. So this is the value of IDC. So that is IDC value is we have got IDC value as Im by pi. This is nothing but the average value of DC current, or else the DC output current is represented by Im by pi. And similarly, we have to find out VDC. So we know that VDC is a voltage, that is DC voltage measured across the load resistor. So which is given by IDC into RL, which is given by IDC into RL. So IDC already we have calculated Im by pi into RL. So where we have seen that Im is equals to Vm by Rf plus RL. So that is VDC is equals to Vm divided by pi into Rf plus RL into RL. So as I told you that under forward bias condition, the forward resistance offered by the load diode is very less, and it is very much less than RL, and hence I can neglect this one. So in that case, VDC can be given by Vm by pi. If I neglect this one, so Vm by pi into RL. So this one get cancelled. So VDC is equals to Vm by pi. So IDC is equals to Im by pi and VDC is equals to Vm by pi. So these are the average value of output current and average value of output voltage across a load resistor. Now RMS value. So as I told you that in the output of rectifier, we have AC components as well as DC components. Always we are going to measure the AC components with RMS value. RMS value nothing but root mean square value. Root mean square. Mean is nothing but average, as we have found just now, average value, and to that we need to take a square, and to that we need to take root. That will give you root mean square value. So now let us find out the root mean square value of load current, that is IRMS, and the formula of that is given by 1 by 2 pi integral 0 to 2 pi IL square d omega t. This 1 by 2 pi integral 0 to 2 pi represents the mean value, and this is the square value, and to the power of 1 by 2. This is root. That is root mean square value. So here, now let us substitute this one. Again, I want to divide the limits here. So that is, only we have to consider for 0 to pi, because for pi to 2 pi, the current is 0. So that is Im square sine square omega t d omega t to the power of 1 by 2. So now sine square, let us take, to the power of 1 by 2. So now let us take Im square out of the integration because it is a constant. Im square by 2 pi integral 0 to pi. So we can write sine square omega t as sine square omega t as 1 minus cos 2 omega t divided by 2. This is a formula we have in the trigonometry. So just substitute it. 1 minus cos 2 omega t divided by 2 d omega t to the power of 1 by 2. So now just take that 2 out. Im square by 4 pi integral 0 to pi 1 minus cos 2 omega t d omega t to the power of 1 by 2. So now let us apply the integration. Now let us apply the integration here. So integration of constant is x. So here Im square by 4 pi. So omega t 0 to pi. Okay. Minus cos 2 omega t. Integration of cos 2 omega t is given by sine 2 omega t by 2 to the power of 0 to pi and whole to the power of 1 by 2. So now Im square divided by 4 pi. So here pi minus 0. This just we are substituting the limits here. Upper limit minus lower limit minus sine omega t by 2. Sine pi it is 0. Okay. Sine pi it is 0 minus sine 0 is also 0 divided by 2 whole to the power of 1 by 2. So now let us, so IRMS, this is IRMS. So Im square, sorry, to the power, Im square divided by 4 pi into pi, because this is all becomes 0 to the power of 1 by 2. So pi get cancelled. So if you take this out of the, if you apply the root, that is Im square divided by 4 whole root. So that becomes Im by 2. So that is IRMS value is equals to Im by 2. So this is the RMS value of current flowing across the load resistor. So now similarly VRMS. So VRMS can be find out by IRMS into RF plus RL. So here IRMS is nothing but Im by 2 into RF plus RL, where RF is very much less than RL. So I can neglect this one. So VRMS is equals to Im by 2 into RL. And similarly, you can substitute even Im is equals to Vm by RL by considering this condition. So VRMS is also equals to Vm by 2 into RL into RL. So this one get cancelled. So VRMS becomes Vm by 2. So this is the RMS value of voltage across the load resistor. So that is Vm by 2. So we have just found the average value of output voltage and RMS value of output voltage across the load resistor. Now let us find the efficiency. So for any circuit, in order to work, in order to give its better performance, the efficiency must be calculated. Efficiency must be very high for the better working condition of any device. So any circuits need to be efficient in its working for a better output. So to calculate the efficiency of half wave rectifier, so first of all we need to measure the, the definition of rectifier efficiency is, it is defined as the ratio of DC power delivered to the load to the AC input power from the transformer secondary. I hope you understood. So we are getting the AC input from the transformer secondary and we are measuring the output voltage, that is DC output power across the load resistor. So that is why efficiency is defined as a ratio of DC power delivered to the load to the AC input power from the transformer secondary. So that is given by PDC by PAC. So in order to calculate the efficiency of this half wave rectifier, first we need to calculate the DC output power delivered to the load resistor and the AC input power from the transformer secondary winding. So first of all, let us calculate the PDC. Let us calculate the PDC value. So we know that power is represented as V into I, that is also represented as V square by R, or we can also represent it as I square into R. V square by R or I square into R. So now PDC is nothing but the power, DC output power delivered to the load. So this will be calculated when the DC current is flowing through the load resistor, and hence DC output power delivered to the load is given by IDC square into RL. IDC square into RL. And similarly PAC. So I already told you AC is measured in terms of RMS value, whereas DC is measured in terms of average value or else DC value. So here now we can also write this one as IRMS square into RF plus RL. RF plus RL. So where we need to consider that RF is very much less than RL. So and hence PAC can also be given by IRMS square into RL, because RF is very negligible when compared with RL. So if I neglect this one, IRMS square into RL. So now just substitute this one in the above equation. So already you know that IDC value, that is Im by pi, and IR and IRMS value, which is given by Im by 2. If you substitute these values in this equation, so that is efficiency is given by PDC divided by PAC, which is equals to IDC square into RL divided by IRMS square into RL. So just substitute the values of IDC and IRMS in this one. So that is Im by pi whole square into RL, Im by 2 whole square into RL. RL get cancelled and Im get cancelled. So here 1 by pi square divided by 1 by 4. So we'll get 4 by pi square. So 4 by pi square, if you calculate, that is 4 divided by 3.14 whole square, you will be getting the efficiency as 0.406. So always the efficiency is calculated in terms of percentage. So efficiency in terms of percentage is given by 0.406 into 100 percentage, that is given by 40.6 percentage. That means the efficiency of half-wave rectifier is 40.6. That means in the given AC input power from the transformer secondary, only 40.6% is going to be converted into DC. So that means the efficiency of the half-wave rectifier is very less. It is even less than the 50%. So this is half-wave rectifier efficiency. The other factor which is to be evaluated in order to analyze the performance of the half-wave rectifier is ripple factor. So what do you mean by ripple? So as I told you, the rectifier output consists of AC components and DC components. So the AC components which are unwanted. Why I am saying this is unwanted? Because I need only DC from the power supply. So I just want only DC components. So where AC is to be removed, and hence AC are said to be unwanted. And these unwanted AC components are also called as ripples. So the rectifier, as a rectifier contains some amount of AC components present, and it is also called as ripples. So the ripple factor is mainly used to find out the amount of ripples present in the DC output voltage of the rectifier. So and hence it is defined as the ratio of effective value of AC components of voltage or current to the direct value or average value of the output voltage. So that is given by, that is represented with gamma, and it is given by ripple voltage to the DC voltage. So the ripple voltage, it indicates the AC component. So that is why we always measure it in terms of RMS value. So that is RMS value of AC component of ripple voltage, which is represented with VRRMS. This is nothing but RMS value of ripple voltage present in the DC output voltage of rectifier, and DC value of output waveform or its output voltage, which is represented with VDC. So now let us find out VRRMS. So if you subtract the DC component from the AC component of the output voltage, then we can have the RMS value of ripple voltage. So that is why VRRMS, as we are finding out the RMS value, so under root of VRMS square minus VDC square. So just substitute that in this formula. So under root of VRMS square minus VDC square. So just take this denominator into the square root. Then it becomes Vrms square minus Vdc square divided by Vdc square. So if I separate them, Vrms is Vrms by Vdc whole square minus 1. So this is the formula of ripple factor which you have to remember. So this is the formula. Now we have already calculated Vrms and Vdc of half wave rectifier. What is a Vrms value? That is Vm by 2 and Vdc value is Vm by pi. Just substitute that in this equation. Then Vm by 2 divided by Vm by pi whole square minus 1. So here Vm get cancelled, under root of pi square divided by 4 minus 1. So which will give you 1.21. So it is nothing but under root of 3.14 whole square divided by 4 minus 1. So which is nothing but 1.21. So it indicates the ripple factor is ripple factor of half wave rectifier is 1.21. So means what? So that is, if you are calculating it in terms of percentage, that is 121%. So it indicates that in the output of rectifier, 121% of AC components are present. AC components, or else we can also call them as ripples. 121% of ripples are present in the output of half wave rectifier when compared to the DC. So this is the ripple factor. So which is very high. For a better performance, the ripple factor must be very low. And what about the efficiency? Efficiency must be very high, but it is very low in case of half wave rectifier. We can say that these two are the drawbacks. Ripple factor is high, which indicates that much amount of AC components present in the output, DC output, whereas efficiency is less. That means in the given AC input power, only 40.6% are going to be converted into a DC component. Now the next factor is regulation. So here, in order to design a regulated power supply, there should not be any variations in the DC output voltage with respect to the load current or load resistance. That means even though there is a change in the load current or load resistance, it has to provide a constant output voltage. So now this is related to the regulation. So based on this, we can define a factor called as percentage regulation, that is defined as the variation of DC output voltage with a change in DC load current is defined as a regulation. As I told you that we should not have any change in the output voltage, even there is a change in the load current or load resistance. So that is why we are defining the regulation as that means it is defined as the variation of DC output voltage with the change in DC load current or DC load resistance. And always the regulation is calculated in terms of percentage. So the percentage regulation formula is given by V no load minus V full load divided by V full load. What do you mean by V no load? That means this is the output voltage when no load resistor is connected. Whereas this is the output voltage when a load resistor is connected. Whatever the voltage we are getting at the output, that is represented with V full load. So here, for the better performance or else for the better DC regulated power supply, always you remember percentage regulation must be very less. So if the percentage regulation is low, then it is said to be a good power supply. That means the performance of that good power supply, that power supply is very good. So for a better regulated power supply, the percentage regulation must be very less. That means there should not be any variations in the output voltage, even there is a variation in the load resistor or load current. It has to be constant. Next, coming to the transformer utilization factor. So transformer utilization factor means as a transformer is providing some AC supply, how much power AC power is going to be utilized while it is being converted into DC output power. That is defined by the transformer utilization factor. So basically it is defined as the ratio of DC power delivered to the load to the AC rating of the transformer secondary winding. So that is PDC divided by PAC rated. So here PAC, generally I told you that PAC is calculated always by considering RMS value into consideration. But here at the transformer secondary, we are getting full cycle of input, that is Vm sine omega t. But we have found Vrms value. This is only for the output waveform which is having only a positive half cycle of output. So this Vrms value is Vm by 2. So now we are calculating AC rating of the transformer secondary where we have 2 cycles. So this RMS value will not be taken for the calculation of power PAC rated at the transformer secondary, because these two waveforms are different. It is having 2 half cycles whereas it is having only 1 half cycle. So if you find out the RMS value for this one, that is given by Vs RMS. Let us indicate this one as Vs RMS. That means RMS value of voltage at secondary winding, that you are going to get it as Vm by 2. How to calculate this one? We can calculate this one, that is Vs RMS can be calculated by 1 by 2 pi integral 0 to 2 pi 0 to 2 pi Vs d omega t, Vs square d omega t. Okay, so what is this one? It is having both the cycles, positive half cycle and negative half cycle, to the power of 1 by 2. So 1 by 2 pi integral 0 to 2 pi. We can represent this as Vm sine omega t whole square d omega t. This is for 0 to pi, and pi to 2 pi minus, because we have negative half cycle during pi to 2 pi, sine omega t whole square d omega t to the power of 1 by 2. So here this again becomes positive. So if you find out the value of this one, you will be getting this Vs RMS value as Vm by root 2. Whereas IRMS, so on the IRMS will be considered as Im by 2. Why? Because here Im by 2 is a current, that is RMS value of current flowing through the load resistor, and this flows only during the positive half cycle, whereas during the negative half cycle it becomes 0. So that is why IRMS should be considered as Im by root 2, whereas this will be root 2 you will be getting, and this you will be getting as Im by 2. Okay, so this will be Im by 2, and hence we can calculate the transformer utilization factor, that is PDC divided by PAC rated. Okay, that is at the transformer secondary. VDC into IDC divided by Vs RMS into IRMS. So that is given by, so just substitute the values here. Vm by pi, Im by pi divided by RMS values. So that is Vm by root 2 into Im by 2. So this one get cancelled. So 2 root 2 divided by pi square. 2 root 2 divided by pi square. So if you find out this value, you will be getting this value as 0.287. This is the transformer utilization factor. This is the transformer utilization factor. That means the transformer utilization factor of a half wave rectifier is only 28.7%. That means only 28.7% of input power is getting used while converting it into DC. Okay, so only 28.7% of input power from the transformer secondary is being converted into DC. So this is also very less. We can also consider it as a drawback of full half wave rectifier. Now the next factor is peak inverse voltage. So as you already know the definition of peak inverse voltage, it is a maximum reverse voltage that a diode can withstand without any damage. Under reverse bias, whatever the diode that can withstand without any damage is known as peak inverse voltage. So when in a half wave rectifier, the diode is reverse biased during the negative half cycle. When it is reverse biased, it is open circuited and hence no current flows through the load resistor and hence the output voltage is considered to be zero and the total voltage of the negative half cycle, which is minus Vm, is going to be dropped here. So that means this will be the maximum voltage that a diode can withstand without any damage. So beyond this, if we increase the input voltage, the diode will get damaged. So the peak inverse voltage of a diode in the half wave rectifier is equals to Vm. Okay. Now coming to the form factor, this is another factor which is going to define the performance of a rectifier. So it is defined as the ratio of RMS value to the average value. So RMS value always represents the AC components and average value always represents the DC components. So it is going to find out the absolute values of the absolute value of all the points of the waveforms. Okay, so that means it is again finding out the amount of AC present in the DC output. So here RMS value you can find, you know that is Im by 2. Either you can take the voltage or current. RMS value of voltage or current to the average value of voltage or current. Im by 2 divided by M by pi. So this Im get cancelled. So pi by 2 which is given by 1.57. So this is the form factor. So that means 1.57, it is also indicates high. Form factor should be less because it represents the amount of AC components present in the DC output. So it is also considered to be a disadvantage of half wave rectifier. Now the other factor is peak factor. It is defined as a ratio of peak value to the RMS value. That means in the AC components, what is the peak value of that AC components present in the output of rectifier? So that is defined by the peak factor. So the peak value should be less. That means ripple value should be less, then it indicates it has less amount of AC components. So here, as it is defined as a peak value to the RMS value, the peak value of output voltage is given by Vm and average value is given by Vm by 2. Vm get cancelled. So 2. That means peak value of ripples present in the output is equals to 2. So this is also a drawback. That means it is having high peak value. So it is also considered to be a drawback of half wave rectifier. So this is about the mathematical analysis of half wave rectifier. So now let us have a discussion on advantages and disadvantages of half wave rectifier. So the advantages we can observe from the half wave rectifier is it is simple, easy to construct and even cheap. So why it is simple? Because it is having very less number of components. One transformer, one diode and one resistor. So as less number of components are involved, so it is simple to construct. Even the cost is also less because of less number of components are used here. And here there is no complexity. So that is why it is easy to construct. All the components are connected in series. So it is simple to construct, easy and cheap. Now coming to the drawbacks of half wave rectifier. So the drawback that we have observed here are the transformer utilization factor is very less, that is 0.287, and it produces low DC output voltage which is Vm by pi, and DC saturation of transformer core resulting in magnetizing current and also some hysteresis losses, and generation of harmonics. Harmonics are nothing but these are the harmonics. So as the output is resulting some harmonics, it is some disadvantages. And the DC output power rectification efficiency is very less. As the DC output power is less, so the rectifier efficiency is also less. So this is one of the major drawback, and this is mainly due to the fact that it is only able to rectify positive half cycle of AC input voltage. The negative half cycle is completely removed. And the other drawback we can observe here is the ripple factor is very high. That is 121% or else 1.21. And one more drawback, that is an only allow a half cycle through per sine wave, and the other half cycle is wasted. That means we are just removing it. Even it is passed, it is getting wasted. So it leads to a power loss. So these are all the drawbacks of half wave rectifier. So, and the advantages are, this is simple, easy to construct and cheap. But as this is having that means a large number of disadvantages, we cannot use this for designing of regulated power supply. We can use this for simple applications like battery chargers and all. So that's all for today. Thank you one and all. I hope it is clear to everyone. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.